In this lesson, we're going to talk about how to balance equations. The concept of balancing equations really rests upon a law that you've probably heard of before, the law of conservation of matter. Put simply, this says that in any ordinary chemical reaction, atoms are neither created nor destroyed. In practical terms, that means that all of the atoms of the reactants, the starting substances in an equation, must be accounted for in the final products, the final substances of the reaction, which we call the products. That means every single atom of every single element needs to be the same. It could be rearranged differently, but the total number of atoms of each type has to be the same. We write chemical equations with reactants on the left side of an arrow and products on the right side. This is important to know for formatting. Reactants, and then an arrow, and then products. If you have more than one reactant and more than one product, you simply write those formulas and put a plus in between them. Here's an example. CH4 and O2 react to become CO2 and H2O. If we do an accounting of the atoms of each type in this equation as it's written right now, you'll notice that there are more hydrogen atoms on the left side of the equation. You see the 4 hydrogens within CH4. Then you see on the right side, there's 2 atoms of hydrogen on the right side. So that's out of balance. There are also more oxygen atoms on the right side of the equation. If you look on the right side, there's 2 oxygens from CO2 plus another 1 from H2O. That's 3 in total, compared to the 2 oxygen atoms on the left side of the equation. Thus, we have to say this equation is not balanced as it's written, and it is not a proper equation. To make the equation balance, to make the number of atoms of each type balance on either side, you may change the number of molecules by adding coefficients in front of their formulas. But you may not alter the formulas themselves. That is, you may not change subscripts within a chemical formula. By the point you've gotten in your writing of chemical equations that you've got good formulas, you can no longer change the formulas. So for example, if we go back to the top here and say, I notice that there's more hydrogen atoms on the left side of the equation than on the right side, you are not free to change water's formula from H2O to H4O in order to make the equation balance. H4O is not a substance that has properties anything like the water that you're supposed to have written in the equation. So what we can do is put large numbers out front. See these red numbers in front of the formulas? They're different from the subscripts that are within the formulas. The big red numbers are called coefficients. Notice that with these coefficients, the number of atoms on both sides of the equation are balanced. That is, if we count up the total number of oxygens on the left side, we have 2 molecules of O2. That gives us a total of 4 oxygens on the left. And on the right side of the arrow, there's 2 oxygens from CO2, plus, because of the 2 H2O molecules, there's another 2 from H2O. That adds up to 4. The oxygens are balanced. What about the hydrogens? Well, just like before, there was 4 hydrogens on the left side from CH4. And on the right side of the equation, because of the coefficient 2 in front of H2O, we have 2 times 2, or 4, hydrogen atoms on the right side. It balances. We made this equation balance not by changing formulas, but by changing the coefficients. The formulas, all the molecules stayed the same. Sometimes it's helpful to draw this out. In fact, in class, we'll have you draw this out. The C is represented with a black sphere. There's white spheres representing hydrogen and red spheres representing oxygen. If you count up the black spheres, there's 1 on the left side of the arrow and 1 on the right. If you count up the total number of white spheres, there's 4 on the left and 4 on the right. If you count up the total number of red spheres, there's 1, 2, 3, 4 on the left, and 1, 2, 3, 4 on the right. Everything is balanced and everything has a proper formula. Let's do another couple of sample problems. If I give you these equations and I ask you to balance them, you might say, okay, let's tackle the top one first, SiO2 plus HF. Yields, when you hit the arrow, you say yields, SiF4 and H2O. Right off the bat, I can see that there's a problem with the Fs. I can see 1 fluorine atom on the left side and 4 on the right, so I need a lot more fluorines on the left side. We also see an imbalance in the hydrogens. There's 1 on the left and 2 on the right. And the oxygens, there's 2 on the left and only 1 on the right. If we put a coefficient 4 in front of HF and a coefficient 2 in front of the H2O, notice we did not change any formulas, then we make the atoms balance. Now we've got 1 silicon on the left side and 1 on the right. We have 2 oxygens on the left, and because of the coefficient 2 in front of H2O, 2 oxygens on the right. We have, because of the coefficient 4 in front of HF, 4 hydrogens on the left side. And because of the coefficient 2 in front of H2O, 2 times 2, 4 hydrogens on the right side. We have a total of 4 fluorines on the left side, 4 Fs, and within SiF4, there's a 4. So fluorines balance, hydrogens balance, oxygens balance, silicons balance. This is a balanced equation. Let's take a look at the one on the bottom. K plus H2O yields H2 and KOH. There's 1 K on either side. There's 2 hydrogens on the left. Notice that hydrogen appears in 2 places on the right side of the equation, both in H2 and there's another H within KOH. So there's 3 hydrogens on the right side. There's 1 oxygen on the left and 1 oxygen on the right. So our hydrogens are out of balance, and we need to do something about that. Consider this. The coefficient 2, 2, an implied coefficient of 1, and a coefficient of 2 would make this equation balance. 2 potassiums on the left side and on the right side. 4 hydrogens on the left side. And because hydrogen appears in 2 places, you have to add it all up. There's 2 in H2. And because of the coefficient 2, there's another 2 from KOH. That's 4 altogether. There are 2 oxygens on the left side because of the 2 in front of H2O. And on the right side, because of the coefficient 2 in front of KOH, there's also 2 oxygens. Everything balances in this equation. There's one other thing that's important to talk about. Some substances exist as clusters of 2 atoms of the same type bonded together. We've talked about this before back in Unit 2. We call these the diatomic molecules. Any of these 7 elements, when you find them in a chemical equation, they will take a subscript 2, and you have to be able to recognize them. Hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. Arranged in this order, you can pronounce them Hofbrinkel. If you look on your periodic table, you would find that 6 of the 7 are kind of in the upper right corner of the periodic table, and hydrogen's on its own in the upper left corner. However you want to remember this is fine, but you do need to remember. When they're alone, they take the subscript 2. But please note, these elements can still be part of other compounds when their subscripts are not necessarily 2. Like HF, well, that consists of hydrogen and fluorine, but their proper subscripts within that formula is a 1. It's not a 2. It's only when hydrogen or when fluorine are alone that they would take the subscript 2. Or take KBr. KBr contains bromine, but the proper subscript for bromine in that compound is a 1, not a 2, because the bromine is in a compound. It's not alone. All right, try this sample problem. We're going to go from words all the way to a balanced equation. Carbon and hydrogen react together to form carbon tetrahydride. So let's think. Carbon. You would look up on the periodic table and write the chemical symbol for carbon. Easy. It's just C. Look up on the periodic table and find hydrogen and write its chemical symbol. It's H. But hydrogen is one of the diatomic molecules. So the formula for hydrogen alone is not simply H. It's H2. Next, we look at the name carbon tetrahydride, and we think, okay, I know nomenclature for binary covalent compounds. I know that prefix tetra means 4. So carbon tetrahydride means 1 carbon and 4 hydrogens all bonded together. So one way to do this, I think this is a nice baby step. You can write the words carbon plus hydrogen yields carbon tetrahydride, and then think, okay, I know symbols, C for carbon, H2 for hydrogen because it's diatomic, and CH4 for carbon tetrahydride. Now, that equation is not balanced. There's only 2 hydrogens on the left side, but there's 4 on the right. So we stick a coefficient 2, a big number 2 in front of the H2 to give us 4 hydrogens on the left side. You can also draw this out, which I think is really helpful. The black sphere represents carbon. The white spheres represent hydrogen. And if you were to count it up, you'd say, okay, there's 1 carbon and 4 hydrogens on the left side. And in one big molecule, 1 carbon and 4 hydrogens on the right side. To balance equations, think about this. It's more of a puzzle than a step-by-step process. You have to really think about all of the elements that are present. Therefore, I can't give you a step-by-step list of things to do to always end up at a balanced equation, but there are some general principles that are worth remembering. To write balanced equations, first list good formulas for all compounds. Remember the diatomic molecules. If they say hydrogen, you've got to write H2 rather than just H. Or for fluorine, you would have to write F2. Any of those diatomic molecules, you've got to remember them. 2, write an unbalanced equation. Write reactants on the left side of the arrow, write products on the right side of the arrow. 3, attempt to balance. When you do that, balance 1 element at a time, and generally start with the more complicated molecules and end with diatomic molecules or atoms that are alone. Those are easier to balance because by putting a coefficient in front of them, you're only changing the atom count for 1 thing. As you do that, only change the big numbers out front of the formulas. Do not change the subscripts within a formula. And then lastly, check your equation. Perhaps draw it out. I think drawing it out is a wonderful way to check your work. As you check your equation, ask yourself, do the same number of atoms appear on both sides? Are the coefficients written in the lowest possible ratio? What I mean by that is, what if your coefficients are 2, 4, and 2? Those are all divisible by 2. So you could take a 2 to 4 to 2 ratio of molecules and reduce it to a 1 to 2 to 1 ratio. If you can reduce the ratio of coefficients, you should do so. All right, students, good luck on the homework.